All right, what'd you get? I have 5.9 times 10 to the minus 10. Did I do that right? Yep. Okay, good. Okay. All right, so to kind of summarize what we saw there, if you have a salt with a cation with neutral properties, like the sodium we just saw in our sodium acetate, and whose anion is the conjugate base of a weak acid, then the solution is going to be basic. All right? So to summarize that a little bit more, a salt containing the conjugate base of a weak acid makes a basic solution. Okay. All right, so what if we have a salt that contains the conjugate acid of a weak base? It's going to make an acidic solution. So here we have the ammonium chloride salt. So when you put that in solution, it forms ammonium ion and chloride ion. Remember, all ammonium salts are soluble. So chloride will not affect the pH of the solution. If you were to react it with water, it would quote unquote form HCl, which we know is a strong acid, therefore it won't affect the pH. NH4 plus, though, will affect the pH of the solution. So if we write out our equilibrium with water, what will form is NH3 and H3O plus. And so because we have H3O plus on the product side, that means the solution will be acidic. Okay? Make sense? You're going to want to practice these. Okay? We're going to skip this. This is basically doing the same thing, writing the expression for ammonium, write the Ka, and then calculate the Ka. You do need to know that the Kb for ammonia is 1.8 times 10 to the minus 5. Coincidentally, very similar to acetate. Okay. All right, so again, to summarize this, if you have a salt with an anion that has neutral properties like the chloride or bromide or iodide, okay, and whose cation is the conjugate acid of a weak base, then the solution will be acidic. Okay, so salts containing the conjugate acid of a weak base makes an acidic solution. But what if we have a salt that contains the conjugate acid of a weak base and the conjugate base of a weak acid? Now what happens? This is a little bit more complicated. So what we need to do, and we've seen how those things affect the pH. So we saw it with acetate. We put that in water, and it forms acetic acid and OH minus. We put ammonium ion in water. It forms ammonia and H3O plus. So the OH minus and the H3O plus are competing with each other. They would react to form water. Okay? But the question then becomes, is one of those in excess? If one of these ions is in excess, then the solution will be acidic or basic. Okay? Now you could go through and calculate the concentration of hydroxide, given an initial concentration of acetic acid, and given the initial concentration of ammonium, calculate hydronium ion. But we can also look at the Ka and Kb values that are associated with these equilibria. So we can compare the Kb for the conjugate base and the Ka for the conjugate acid, and come up saying is that this reaction, one with the Ka associated with it, is occurring to a greater extent than this reaction, which means that H3O plus will be greater. Okay. For the ammonium acetate solution, because Kb and Ka are equal, a solution containing this salt would be neutral. Okay, it's not always the case. This is actually kind of a special case. Questions on that? Okay. How are we doing? Okay. With a prediction. So in this case, okay, we have both a weak acid, salt of the weak acid and the weak base. If Ka is greater than Kb, then it's acidic. And so with that, if Ka is less than Kb, then it's basic. All right? And if Ka is equal to Kb, then it's neutral, a neutral solution. Okay. So here. All right, I'm also going to make a video of this slide. What is the pH when the following salts are put in solution? So your approach should be to determine the ions and if they can react with water. If they do react with water, figure out if they're going to make OH minus or H3O plus. Okay? So I will tell you though, ammonium nitrate, acidic. Sodium fluoride is going to be basic. Potassium chloride will be neutral. And sodium carbonate will be basic. Okay, and again, I'll post a video walking through each of these things. This is sort of a similar question. So if you have an unknown salt, you put it in solution, and you measure the pH. I think this is what you're doing in lab in a couple weeks. Okay? You're going to identify a salt based on its acidic, basic, neutral properties. So if the salt ends up being neutral, you need to find the salt that wouldn't affect the pH in any way. And in these examples, that's going to be potassium bromide. Okay? I'll let you go through those. All right, so let's actually do a problem here. Yep.
Can you be posting like these problems before the end of the day so we can get the help with the homework?
I'm gonna try to, yeah. Well, you know what? I have this one as well because I apparently did not prepare this in my notes, and I don't necessarily. I think I didn't. Let's just do this one. I'll post a video. I really want to go through the whole thing like that. So here we have a solution of pyridinium bromide. We're going to have 0.1 moles of it, and we're going to dissolve it in a liter of water. So it's going to be 1 mole per liter. And we're given a Kb value for this, for the weak base. Okay. So if you didn't know this was a weak base, this is the clue. You got a Kb for pyridine. Okay. Or if you didn't know what was in solution. Given this formula, so this is kind of complicated, right? What it's going to form. So we're going to have C5H5NHBr. We're going to put this in water. It's going to completely dissociate to form C5H5NH plus Br minus. Okay, that's not our equilibrium that we're worried about. I'm just showing you the ions that are formed. We know that bromide is the conjugate base of a strong acid. It's not going to affect the pH. We're not going to worry about it any more than this. Okay? So what we're going to worry about is the pyridinium ion. So we're going to take our C5H5NH plus, and we're going to react that with water, make an equilibrium. And we're going to form the base pyridine. Okay, so that's given in the problem. C5H5N plus H3O plus. Okay? So everyone okay with that? Even this is hard, yes. Oh, yeah, no, I think that was a brain fart. Point 1. Yeah, thank you. Other questions? Okay. All right, so just like we do with other weak acid, weak base problems, we're going to set up an ice table. We're going to have an initial concentration of the pyridinium ion of 0.1 molar. 2 zeros there. We don't worry about water, and we don't have any products in solution initially. Okay? Because we don't have any products, we know that we're going to form products as we achieve equilibrium. So we're going to have minus X for our reactant, plus X for our products. So at equilibrium, we're going to have 0.1 minus X of pyridinium ion, X moles per liter of pyridine, and X moles per liter of hydronium ion. Okay. We were given a Kb value. Is that going to be useful in this case? No. We actually need the Ka value because we have an acid on the reactant side. So we need Ka. So we can calculate our Kb based on Kw equals Ka times Kb. Oops. Calculate our Ka, excuse me. So that's 1 times 10 to the minus 14 divided by 1.7 times 10 to the minus 9. And I end up with a Ka of 5.9 times 10 to the minus 6. And that's going to be equal to our concentration of products, C5H5 and H+. Oops. Erase. Times, oh, nope, I'm sorry. C5H5N times H3O plus divided by the pyridinium ion, C5H5NH plus. Okay. And so we know these values at equilibrium, x squared in the numerator and 0.1 minus x in the denominator. So I'm always going to, as I do these problems, want to make an assumption that x is smaller than our initial concentration. And so we can check that. We'll take our 0.1 divided by 5.9 times 10 to the minus 6. Oops. I end up with a very large number of 1.7 times 10 to the 4th. So assumption is valid. And so we can do 5.9 times 10 to the minus 6 is equal to x squared divided by 0.1. All right. Everyone okay with that? Okay. Let's figure this out, and then we have 5.9 times 10 to the minus 7 equals x squared. Take the square root. 7.68 times 10 to the minus 4 molar. This is equal to the hydronium ion concentration. So we'll take minus the log of that. And the pH I get is 3.11. So make sure you get an acidic answer here. Really common, easy mistake to make is using Ka or Kb when you should be using the other one.